you guys might have written parallel algorithms, at least at a scale of multi-core programming, and maybe even on Hadoop-like systems. What you guys need to, I'm going to sit because hopefully it'll record better. The key issue is how do you actually analyze? So I'm going to go through some very, very simple ideas and try to see how do we analyze, given a problem, given an algorithm that needs to be parallelized, which is essential when problems are too large and we can't fit them into a single machine. How do you actually go about doing that? How do you analyze what can be parallelized, to what extent, and what kind of changes might be required to do this? So, the most important aspect is parallel thinking, which is sort of what I would like to encourage from via today's lecture, is that you guys are used to thinking, whether it is when you consider algorithms or when you even start coding things up. Because of how we have been trained, there is a sort of a bias, and most people end up thinking sequentially. Do things in a specific way, right? A for loop where I'm doing one thing after the other. What you need to do is to change that and start thinking in a parallel fashion. What happens when there are multiple computers operating together? When you think about this, can you actually dim down the lights? So switch those and turn on the other one, the slider, yeah. Turn those on. Yeah, can you increase the brightness of those? Yeah, that's probably better. So Seymour Cray, who was sort of the father of supercomputing, very famously said, this is before he started actually making large parallel machines. He did this comparison, so if you're plowing a field, what would you rather use? Would you use 2 strong oxen or 1? Or would you go for using 1,024 chickens? Now, if you think about this, it seems like a bad comparison. Yes, ideally we would prefer a strong oxen or a single strong ox even. And one way to think of it is as having a really powerful single core machine. So you have a really fast, and this is sort of the direction we were going in a few years ago, where you had you had the gigahertz race. I had a 2 gigahertz machine, I had a 3 gigahertz machine, and then you sort of were hitting 4 and then it all flopped out. But the physical limits to how strong we can make a single processor. This is easy because it's sort of performance that you get for free almost. You have a piece of code that runs, which takes 5 minutes now, and maybe 2 years later you get a faster processor, now it takes only a minute. You don't have to change anything because everything is easy. It's like going down to a shop and buying a new ox, which is stronger and bigger and everything else. What is the problem with this is that when you think of a case, assume that 1,000 chickens are actually, as far as their strength is concerned, equivalent to an ox. The problem is not that, why do you intuitively think of it as being a bad idea to try to plow a field with 1,000 chickens? Any suggestions, any ideas why? You all agree it's a bad idea, right? Why?
Not strong enough to throw the field.
No, we made that assumption that 1,000 chickens, you pick whatever number that together is going to be the equivalent of whatever the one ox is capable of pulling. So we sort of bypass that. Maybe 1,000 is not enough, maybe you need 1,000,000, I don't know. But
Maybe it is costly. Controlling one of these.
exactly. So it's a matter of making sure that they all work together, right? It's sort of like saying that you have a torch and I have a beam of light versus laser, right? Where everything is synchronized and efficient, and therefore you're able to burn things with it, right? So the question is, yes, they are kind of equivalent and maybe it'll work better, but in many cases, like especially when you want them to do a dedicated task, synchronization is important. Making sure that they're coordinated well is important, and that is difficult. Whereas, now you can think of a different application. Let's say that you have, and actually this is a real situation where people actually use it in California nowadays. Assume you have large fields and you want to control forest fires, which are a big problem. And I say that an easy way to do this is get a bunch of mountain goats and let them just run and mow down all the shrubbery out there, grass and everything else, which is a potential for forest fire. That is not that problem. Why? Because you don't care about synchronization as such. As long as all of those goats, it's not like you want the goats to go through or graze on these fields and mountains in a particular order. It doesn't matter, it's what we would call as embarrassingly parallel. I can just randomly scatter them around, they all operate in a small area and they're fine. If, let's say, you had a field and there were grains scattered on it, and I wanted to, instead of cleaning it up, here you go, 1,000 chickens left out there, give them some time, they'll wipe it clean. Because they don't need to synchronize that much with each other. They're all eating small bits at the same time. So what is important here is to understand in which situation the ox is going to be better, and in which situation a lot of chickens which are individually weak are going to work better. But is that the only solution we have? If you want to, let's say in this case, plow an oxen. I'm going to give a counter argument here to Seymour Cray, mainly because he goes with this example, is that you can actually do better, which is that you develop better algorithms, things which are not constrained by the same aspects. In this case, it will be you build a tractor, you come up with a tractor. It's a different way of doing things. And fundamentally, that's what you're going to see. If you think from the perspective that I used an oxen to, or basically saying that I used an animal to plow my fields, and the only option now I have if I need something stronger is to double them or increase, add 4 of them or 1,000 of them, then you're limited. In many cases, when you have to think parallelly, and these things might be forced on us by different reasons, like where the architecture is going. Most of you are not hardware engineers, so you're not necessarily making this. There's so many factors which go into this. So given a set of architectures, the way, whatever is the most current form of the large machines that are available, what you need to do is to say that algorithmically, how do I do it? If you start from how you were doing it on a single core machine, it's not going to scale and it's not going to work, and it's going to look as stupid as saying that I want to go from a single ox to 1,000 chickens. What you need to do is to think outside the box, and in most cases you will probably have to redesign your algorithm. And so that's what you should think of. I just dumped this here. I'm not going to talk too much about it. I want you to think. This is fundamentally, it's a very simple problem. Let's say that we have an array with n elements, right? And our goal is to compute the sum of all of these elements, maybe with some function applied to each element. In this case, the square root. What all do you need to consider when you take something as trivial as this? All of you can write 2 lines of code in 2 minutes, or maybe 20 seconds, in order to do this. But when we think about the implications, when you think beyond that I need to run this on my laptop, what all do you need to consider? And there are a bunch of different aspects here. You have to consider what is the machine model. Why is that important? I'll quickly get to what I mean by each of these, but to put it quickly, if you have these on, say, a machine which has vector instructions, like SSC or something, you're going to go about implementing this differently. If the array is so large that it's not going to fit in your memory, you're going to use a different strategy to do this. If it's so large that it doesn't fit in memory and it doesn't even fit on disk, then you have to come up with other strategies. What is the cost of exchanging information? So when we decide on the right algorithms, at some level, you have to consider what is the target machine that we are going to have to map this onto. We will come something close to this example later, but I want you to think about how it maps onto whatever machine models that you are familiar with. There is also the issue of programming models. Yes, I know that I have it. Programming is where, how do I translate this from this onto the actual programming constructs? And once we have done that, we also have to consider how do we do a performance analysis? How do we figure out if what we have done is good enough? If something is not working fine, is this because there is a problem in the implementation? Is this the kind of performance that we would expect given the method on that particular architecture? Or are we going wrong somewhere? And this is what you need to think. And as we go through some of the examples today, I want you to think about how you would go about doing these things. These are very, very trivial. Many of these problems are so simple that you would don't even think about it. If you go back to this problem, a lot of you probably are exposed to big data in some way. I've thought of Hadoop, right? What is this? You're mapping some function onto this, and the summation out here is sort of a reduction operation. You're gathering it all, right? But again, the complexities of how you actually do it and what it entails is what you should think. Even before you start writing code, you need to start thinking about what would be the best case scenario and what would be the worst case scenario for this. Briefly, most of you probably already know about this. The most common machine model that we use is a von Neumann architecture. This hasn't changed much, and effectively what it says is that there is some input and output which gets operated upon by the central processing unit, which is made up of a control unit. This is what is basically going through your code. The code itself is also stored somewhere. You're fetching one instruction at a time, figuring out what to do next. You have a ALU attached to it, which has an accumulator where operation take place. There is a fixed memory, and then you move both the code as well as data back and forth from this memory. So this is sort of the general thing. And it's sort of always, at a very theoretical level, the fundamental definition is that you can only execute one instruction per unit of time. And this one instruction refers to both the instruction that you want to execute as well as the data. So think of this as the dumbest single core performance that you can think of. The problem that you're going to have is that I doubt if there is any true von Neumann machine in this room. Maybe somebody has somewhere. But because architecturally things are moved so far off that it's really difficult. But then there are so many variations that it's still a good tool when you start analyzing it. And you think of all our parallel machines as having basically being made up of hundreds of thousands of millions of such simple machines. It's just because it makes our life a little bit easier when we analyze them. This is probably the worst summary for characterizing algorithm performance and algorithmic complexity. I'm assuming all of you know it. I'm just putting it on a board. If you don't, please go ahead and read, take some other courses or catch up, because this is going to be required. So the most common way in which we're going to assess algorithmic complexity, this is not actual measurement, but considering the algorithm, not considering the architecture, not considering, maybe sometimes considering the architecture, but not considering the actual programming, is going to be using the big O notation, which is basically saying that if you have an input size of n, we basically want some estimates on total runtime, which I'm giving here by T of n, and S of n, which is the necessary storage. In most of these big data type applications, these are the two important considerations. How long does it take to run? How much storage do I need? And you need to think about it. This is going to be in very abstract terms, but this is again going to be in layers. So the storage is how much RAM do I need? How much disk do I need? How big should my cache be? And depending on exactly what you're doing, you need to understand that. And instead of talking in arbitrary terms or very specific terms of saying that I need 1 gig of RAM, what we're going to be doing is that we're going to be considering the complexity, which basically means that we represent it as a function. And what you would normally see, and you'll see it in the following example, and I hope all of you know this, is that basically it's a lower bound on, it's a upper bound on the complexity, which is that you give it in terms of a function. And what if you express in a big O notation as a function, what it means is that it's the actual runtime in this case, or the storage, is going to be less than or equal to some constant times that function. And why is this important? Is that the constants are important as well, but we are ignoring them here. Because this is how we can say that you can answer questions like, if I double my problem size, what happens? As n changes, what are my expectations from the runtime or from the storage? And if you want to really go very large, you want to make sure that that is linear in most cases. Worst case, n log n. The moment you start hitting things like n square, that doesn't scale. Why? Because for something that you're spending $1, you're going to be spending, if it increases twice, you're going to be spending $4 and $16 and so on. That is something that you don't want. Anything beyond quadratic, which is your order n square, is probably way too bad even in a sequential territory. Constants are important, but constants are going to be important sort of a little bit later down as we get close to the actual implementations and optimizing it, and then choosing which methods are there or are correct for that for our particular implementations. So once we can characterize an algorithm, we can actually start just comparing them based on the function. So we say that n log n algorithm is going to be better than an order n or n square algorithm. And now you might have to start saying that here are two different algorithms to do the same particular task. One which requires n square storage, but will do it in order 1, say, which is constant time with respect to a problem size. Whereas you might have another which is going to now take n log n time and require order n storage. Depending on the kind of problem that you're going to solve, which basically means what is the machine you're going to solve it on, and what is the range of n's that you hope to encounter. If n is really small, and I don't mind having n square storage, maybe it's important for me to use that. But the moment I know that n is variable and it's going to be large, it's not going to work. And this actually happens in hardware. So there are several algorithms where you actually opt for an n square storage for constant term, and you have dedicated storage on hardware for these kind of methods, because that's what is going to work. But it doesn't scale. So in most cases, wherever scalability is important, you need to consider linear or n log type algorithms. I keep talking about scalability, and there are various ways to define it. When you talk about systems, we typically talk about scaling vertically as well as horizontally. Vertically is what used to happen, and everybody was very happy with it, which is, to keep getting faster and faster machines. It gets used even now more from the perspective that I have a larger node. So when you talk about clusters which are being used for big data, like Hadoop clusters, we talk about scaling it up, which means that I put a faster, bigger multi-core CPU there, increase the amount of RAM, maybe add a few extra spindles, and that's what it is. So basically, at a node level, it's become much more powerful, right? The problem here is that depending on what you're doing, maybe memory is fine, but even then with memory you need to deal with, you can't, even when you're arbitrarily increasing your main memory, you still have to deal with a limited cache size. So that doesn't scale directly, it doesn't scale as linearly as you would like it to. CPUs aren't getting faster, so if you're compute bound, scaling up is almost not possible unless you at least parallelize at a multi-core level. The other option which scales well but is harder is to scale out or scale horizontally, which means that you say that I have 10 machines now, I have a requirement for a larger problem 2 years from now. I'm going to increase those 10 machines to 20 machines or 30 machines, depending on the problem size. It's better in some sense because it's more adjustable and you're not necessarily getting rid of your old hardware. The problem here is that not everything scales. So there is a limit to what you can scale to. So scaling something to the order of 1,000 nodes is easy or easier, whereas scaling something to the order of 1,000,000 nodes is much harder, because then you need to change. Ethernet is not going to cut it. You need to make sure that your communication costs are there. Or you have to say that I'm going to stick with Ethernet, but I have to now come up with algorithms which are going to factor this in, that there is an added cost of communicating between any two arbitrary nodes on this. So This is sort of the first consideration that you should think of. What are you realizing? When you start with a problem, assume you're at the threshold of what you can solve now, or maybe you can't even correctly solve the system. In the future, which of these two strategies is going to get you there? And is it something which is feasible? There is another way now. When we talk about scalability, you also want to measure the performance, the efficiency, and the speed up that we get. And this is usually fairly simple. The speed up is basically the best sequential time. So assume it's the case of comparing the oxen to the chicken, or one oxen to 10 oxen. You take the best sequential time and the time it takes on P process, whatever is the number. That is basically your speed up. So I added P times the number of resources. What's the speed up I can get? The other way to look at speed up is efficiency. And the efficiency is going to be always less than 1 because you're going to pay a fixed cost for coordinating or synchronizing between these. If you have a perfectly parallelizable method, then what I call as embarrassingly parallel, maybe like the goats grazing grass, in that case the efficiency is probably 1 or pretty close to 1. The efficiency for the case of chickens plowing a field is going to be very, very bad because they're going to be maybe taking about the same time, maybe it might be even more or much greater than what the oxen would have taken, a single oxen. So when you consider scaling up your algorithms, make sure that you consider both the speed up and the efficiency. Now, this is Amdahl's law. You probably have heard about it, that when you take a particular algorithm and you want to parallelize it, there are sequential bottlenecks. There are parts of the algorithm which are inherently sequential, right? And the percentage of the overall work which is sequential is going to vary depending on what you want to do. This is again something that you should consider at the planning phase, depending on your problem. There is a speed up where if you are given the percentage which is sequential, and that's given by this. As a counter to this, you have Gustafson's statement, which is basically saying that the sequential part, in most cases, this is not universally true, but for a very large set of applications, the sequential part is independent of the problem size. What that means is that you keep increasing the problem size so that your efficiency goes up because of how they're related. So the other way to look at it, and this sort of goes back to the scale, the horizontal and vertical scalability, is that a better way to look at it is that I can solve a particular problem efficiently right now for a given size on a given number of processors. The way I should do it is that tomorrow when you have a larger problem, I shouldn't necessarily try to say that I'm going to get a bigger set of machines and try to use it to solve a bigger problem. What you want to do is to scale out, because you really want a larger number of processors, because that's going to improve your parallel efficiency, assuming that you start with an algorithm where the sequential part is sort of independent of the problem size. But this is true in most cases. And that sort of gives you the other way to analyze it, which is what we popularly call as strong and weak scalability. And you'll understand why it's strong and weak. So assume that we have an increasing number of cores, and I'm using cores in a very generic fashion. So think across your GPU cores to CPU cores to the nodes on a big cluster. Just independent processing unit. This is the level of parallelism. You're increasing the level of parallelism. So we have strong or a fixed size scalability, which basically means that with increasing number of cores, I'm keeping the problem size fixed. Why would you want to do that? For the same problem, why would I want to keep increasing the number of cores? Yeah, this is basically a performance issue, that I'm not happy with how long it takes for me to solve this problem, right? This is hard, and that's why it's strong scaling. Or this is strong to get it perfect, which means that if you have a problem right now, it takes an hour on this machine. If you use 2 machines, it's probably unlikely that it's going to take you half as much time. And pushing that to the limit of the number of processors tending to infinity is almost never there. It's going to plateau out at some point, and that's the fixed cost you're going to have to pay. The other one is actually a little bit easier to realize, which is weak or fixed size scalability, which means that you keep the problem size per processing unit fixed. So this is the other case I talked about, which is that the problem size per computer or per process, per core, whatever unit you're using, is fixed. So if I have a larger problem to solve, I throw in more resources. You can think loosely in terms of how we operate, right? Let's say you're doing physical labor somewhere, right? You want to, I don't know, take sacks and load them into a truck. You have a fixed cost, an idea of how you're going to scale it. It's not like you might, but it's not very efficient to say that I'm going to just have 2 men loading it no matter how big the load is. It's going to take forever and they're going to get tired, and there are other aspects to it as well. So you want to say that the better way to do this is to say that given a core, I have it well analyzed, I'm going to give it a fixed amount of work no matter what. And then look at scalability, because this is really going to factor in what are the issues, what are the challenges here. The challenges here is that the synchronization, the communication, the coordination between them is what is going to factor out in how well or how badly this scales. So again, when you test methods, when you start developing it, consider both of these cases, and it's good to understand and analyze how your algorithm and your implementation scales both strongly and in a weak fashion. Okay. When you consider parallel programming, there are some general guidelines for how you go about doing this. And again, many of you might be sort of familiar with MapReduce. It's sort of a dumbed down version of what you might have to do in many cases. Fundamentally, you can break it down into sort of these 4 or 5 steps. I'll explain these in detail, but just bear with me for a minute. You want to first take the task that you have, and you want to partition it for work. And I say partition work because this might be related to partitioning data or dividing up data, but it might also be at a task level, which is that you're not really necessarily dividing up the data itself, but you're dividing on a particular task because it makes sense. Those of you who have probably done some event-driven programming probably know how to think in terms of tasks, specific functions, specific roles that are. You want to determine the communication patterns. And communication, again, I use in a very generic sense. You have a bunch of tasks, right? How do they need to exchange information with each other? How do they need to synchronize and coordinate? Again, we are doing this completely independent of the architecture, the programming model, even maybe the problem size. You want to agglomerate, and this is sort of the first case where you want to see, am I targeting a cluster? Am I targeting a GPU? Am I targeting vector instructions? What is the kind of parallelism that I need to expose given my partition tasks and communication patterns? And once I've done that, I will map it to the actual processors. So this is sort of a graphical way to look at it. Start with a problem. This is an arbitrary problem. And you can think in terms of the summation of the square root of an array elements, if you want to think of it. You want to first partition it completely into tasks. And this could be like, I need to take the square root of every single element. That's a task, right? Completely independent. Break it down to the extent that you can. Then think in terms of the communication. The computation of the square root doesn't really take that much time. There is no communication, it's completely independent. I'm applying some function to each entity independently. So that's not a problem. The communication factors in when I need to do the sum, correct? And we look at it again in a way. In this particular case, there is no problem. The agglomeration basically says that you take these tasks, which are divided both, like I said, maybe based on data or just on the functional nature of how you're operating on this data, and you have the communication platform. Try to group them together. And the way you do this agglomeration, like I said, is going to depend on what is the underlying architecture that you're targeting. What is the level of parallelism? Is it very fine-grained, as you would see in vector instructions or on GPUs? Or is it very coarse, as you would see on large data processing clusters? And once you have this, you can map each of these agglomerated clusters onto specific nodes or processing units in your whatever architecture you have chosen. Is that somewhat clear at least? And you need to think at this level. When you start off with saying that I have some data and I can simply just scatter it across this, and you need to consider how does your application code, how does your algorithm interact with the data, how do they actually communicate, what are the dependencies? Let's look at some examples here. That's going to be super, super inefficient. If you just had 2 machines, it doesn't matter. If you had 4, you can probably live with it. If you start getting to thousands of nodes, then that's a problem, right? So you need to understand that this is how things are happening. Don't think that when you call reduce on something, it's happening magically and it's a single function call, it's a single execution step. You need to think of how large your network is. Does it make sense? Should I be avoiding that? Right? So you need to think about how what you want to do translates and how it needs to be done in parallel. So, and if you had independent state, it's basically the maximum depth. This is sort of your bottleneck concept that the one which is the slowest is going to dominate. So the depth of your overall algorithm is going to be dictated by the longest chain of dependent executions on any given process. So you need to factor that. Ideally, we go for a very high level of symmetry that the depth is the same on every single unit. That might not always be possible, so you need to analyze that. So let's just, again, hypothetically, it's a very, very trivial problem. Let's consider how you actually do this in a parallel sense. This is sort of a fake language out here. We have an algorithm sum which takes an array A of size n, and I'm going to do a parallel for, right? So this is the iterative model for something which we talked about initially, right? You basically sum, you go from 0 to n by 2 and you add up the counterparts, 2i and 2i plus 1. And you create a temporary variable out here. And then you call sum b on that, right? So this is how you would do this. Let's sort of do the complexity analysis of doing something like this. The depth at each level, right, has been reduced by n by 2. The problem size has become n by 2. And we did a fixed amount of work in each iteration. It's just this one single step, right? So that is order 1. It doesn't matter. What we do at each level does not depend on the size of the problem. So summing this up gives you log n. The work, what is the amount of work? The work got reduced by half, right? Because we started off with an array of size n. This is of size n by 2. So this should really be, sorry, oops. It should really be sum of okay, we're back. So let's talk about something a little bit more interesting. It's not significantly more interesting. It's still along the same lines of adding up a bunch of numbers. How many of you know what a prefix sum is? It's also occasionally called a scan. Anybody heard of what a prefix sum is? So let's see what a prefix sum is. You'll see this, the term scan, at least in the context of parallel algorithms, used almost the same prefix sums. Let's say we have an array like this, which is 4218. It's basically each entry is replaced by the sum up to that point. So the first entry doesn't change. This one is basically, the second entry is 4 plus 2, then it's 4 plus 2 plus 1, 4 plus 2 plus 1 plus 8. Okay? So you're just sequentially. You can think of it as like, when you have a probability distribution, you want to do a cumulative probability distribution. It's basically the cumulative nature of this. Now, I'm sure all of you can easily write a sequential algorithm for this, correct? It's easy? The depth of the sequential algorithm is order n. Is that clear? Everybody sees that? Because you have to go through the array and you're. So the simple way to do it is you keep sort of a sum up to this point, and you keep going and you keep writing it, recording it as you go through this. It's not parallelizable, is it? So you need to change the algorithm, correct? So we just saw how we can sum up numbers. You guys want to think about how you want to do a prefix sum in a parallel fashion. One point to note is that it generalizes to any associative operation. So you can have a prefix product or any such operation. And these are very useful things because in one of your next assignments you will need to use prefix sums in order to be able to parallelize some. So I want you to sort of think about this for a minute. Okay. Muktesh. So, any ideas? Yes.
Break them into subproblems.
Hmm?
Scan the subproblem.
Okay.
And then the solution of the first subproblem should be added to the next all.
Yes, but
So in some sense it's recursive because.
yes, it is recursive. But think again. Yes, you're very close, but you still have the issue of a dependency then, right? How do you recurse beyond that? Unless you have to go again and do it. Half of your solution is correct. The question is, how do you actually update after that? Yes, you break it down all the way, then what do you do? Because one half of this is sort of the sum, right? Because as you get here, this is the sum. So the use, and I'll show you an example of a very sort of, again, a very artificial example of why you need to do this or why it is useful. When you're parallelizing things, like things that you take for granted when you're sequential, I have access to all my data, you will see that are not so easy. And the scan sort of helps you do it. It gives you an idea of the relative position of values that you might have. So let's see. Okay. So here's a sort of a formal definition, right? Input is a bunch of numbers, and we are interested in basically computing another array of the same size where each entry is going to be the sum up to that index of the sums of the input array, right? So this is formalizing it. Sequential algorithm, the best you would do is order n. It's simple. You do a single pass through the array, right? Let's look at work depth, right? What is it that we really want, ideally? You want the work to be order n still, right? You want a work optimal algorithm. Depth, from an intuitive perspective, where you are going, you're dividing, it is going to be log n, right? That's how you're going to divide and conquer. That we know. It's probably difficult because we can't do this. If we could do it better than log n, we would be able to do the sum better than log n, right? This is doing a little bit extra work than simply summing up the array. What are you going to do? There does exist a recursive and an iterative implementation. I'm going to go through the recursive. And again, as you were right, it is a binary tree like the sum. But the key idea is that you actually do two tree traversals, one bottom up and one top down. And you can think of the bottom up being the part which computes the local sums, and the top down which propagates it down to the respective entries so that do it. So this is where complexities are interesting. So yes, the constant is different now. So you're doing two passes over the tree in parallel, which can be a problem depending on how good or how bad your network is. But this is still the best you can do. And it's a very useful algorithm. It's so useful that in a lot of frameworks, you will have vendor specialized, super optimized codes to do prefix sums. So these are things that you should always do. And these are nice also because as you have your own problems, significantly more complicated, you can break them down into these kind of building blocks. And so it's important for you to think. So when you come across a problem like, this is very similar to how you would do a scan or a prefix sum, and so that's how my strategy should be the same. So it's a divide and conquer plus a recursion algorithm. You break the scan in parts, compute subcomponents, and combine. And I sort of just mentioned the idea of what it is. Previous guy is 0, local, added. Previous guy is 6, so this is even, so this is odd, so this guy is copied. Here, you take the previous guy, which is 6, plus add this one. Here, you simply take the previous guy. Okay? So this is going to go and it's going to recurse at the same level. At each level, you either use this entry plus the previous guy or the entry itself. Is it clear? So just let's look at the code once more. So you go through, if it is odd, and again, odd and even is going to depend on your 0 and 1 factoring, but you understand the general idea. Either copy from the previous guy or add a local component if it exists. Okay? Is it clear? So that's why you're reusing the full amount of information. The way you first described it, you would have had to propagate it completely. And so that's why the second pass, again traversing through the tree, is important. Okay? Is this something that you guys want to implement? Okay. Can do that. Yeah. Why don't you guys, I'll probably present this to you during the beginning of the next lecture. Think about how you would do this iteratively. It's a good practice just to think in terms. It's not very difficult, it's not very different, but think in an iterative fashion, how would you do this? You want to use the combination of these two tells me whether it is true, whether it's indeed the value, and what its index would be. Okay, I think I'm going to stop because